Imagine an experiment designed to answer a pressing question: which morning beverage, water, coffee, or a baraka, best cures a hangover after a freshman party? The setup is straightforward. The independent factor is the specific drink assigned to each student, and the dependent variable is their self-reported morning wellness on a scale of 0 to 10. To find the winner, researchers initially run a standard ANOVA to compare the average wellness scores across the 3 drink groups. This is a standard ANOVA output table. The F statistic sits at 1.714, yielding a p-value of 0.199. With a p-value sitting comfortably above the standard 0.05 threshold, the researchers must fail to reject the null hypothesis. Statistically speaking, the experiment is a bust. But this standard analysis ignores a glaring physical reality. It assumes every student woke up on a level playing field, completely dismissing their vastly different states of intoxication. Fortunately, the researchers collected an additional piece of data: a 0 to 10 rating of exactly how drunk each participant actually was the night before. Analyzing experimental data without accounting for unequal baseline conditions easily masks true treatment effects, passing off meaningful biological signals as random statistical noise. This baseline condition is what statisticians call a covariate. It is a continuous variable that influences the dependent variable, even though it isn't the primary focus of the research question. In this case, heavier intoxication the night before naturally leads to proportionately lower morning wellness, completely independent of what beverage is consumed. To fix the analysis, we need statistical control. This is a mathematical technique used to isolate and subtract the variance directly attributable to these outside variables. Analysis of covariance, or ANCOVA, serves as a structural bridge between standard ANOVA and regression models, engineered specifically to execute this statistical control. Applying an ANCOVA shifts the actual research question. It asks what the relationship between the morning drinks and wellness would be if the covariate, drunkenness, were held constant. Mathematically, holding a variable constant means assigning every single participant the exact same average value for their baseline drunkenness. By deploying an ANCOVA to neutralize these uneven baseline variables, researchers can recover lost statistical power and uncover the hidden realities within their data. This is a visual representation of the study's total variance in wellness. To understand how ANCOVA boosts a study's power, we have to look at how this block is divided. Under a standard ANOVA model, the block splits into 2 pieces. We carve out a small slice representing the isolated drink effect, leaving a massive remaining block labeled unexplained error. Because the faint signal of the drink effect is completely drowned out by the sheer volume of that unexplained error noise, the resulting p-value fails to reach significance. The ANCOVA intervenes by carving a large chunk directly out of that unexplained error block, relabeling it as variance explained by drunkenness. Notice the new ratio. The actual drink effect slice hasn't grown a millimeter, but the remaining block of unexplained error is now significantly smaller. Statistical power is a ratio of signal to noise. Shrinking the denominator of error variance mathematically amplifies the power of the treatment effect. ANCOVA doesn't magically increase the strength of a treatment. It simply clears away the baseline noise so the true signal can be accurately measured. This variance reallocation dictates how ANCOVA recalculates group averages to create a perfectly fair comparison. And ANCOVA never compares the raw group averages. The entire test relies on calculating what are known as adjusted means. This scatter plot shows the raw geometry of the experiment. The x-axis represents drunkenness, the y-axis is wellness, and the data points are color-coded into 3 distinct clusters for water, coffee, and baraka. We can draw 3 separate, downward-sloping regression lines running through the center of each drink cluster. These map the exact relationship between drunkenness and wellness for each beverage. If we look at the raw y-axis averages for each group, they are artificially skewed simply based on where their specific cluster happens to sit horizontally on the x-axis. The geometric objective of an ANCOVA determines what the y-axis scores would be if all data points shared the exact same x-axis coordinate. To achieve this, we draw a stark vertical line down the exact center of the x-axis. This is the grand mean of drunkenness. Next, we slide the data points up and down their respective parallel regression slopes until every single point intersects precisely with that vertical grand mean line. Tracing those intersection points over to the vertical axis reveals the new y-intercepts for the three groups. These are the adjusted means. These adjusted means provide a perfectly level playing field. They geometrically simulate a flawless experiment where baseline conditions were perfectly identical for everyone. However, this geometric sliding trick is mathematically invalid if a specific constraint is violated. Statisticians call this the assumption of homogeneity of regression. It dictates that the relationship between the covariate and the dependent variable must be identical across every experimental group. Visually, this means the three regression lines on our scatter plot must remain perfectly parallel to one another. If those regression lines intersect or point in wildly different directions, the parallel structure breaks. Intersecting lines mean that drunkenness affects wellness differently depending on which drink was consumed. That structural inconsistency shatters the ANCOVA model entirely. This table shows how analysts mathematically prove the lines are parallel. They test an interaction term between the independent variable and the covariate, labeled here as drink times drunkenness. The p-value on this interaction row sits at 0.885. In this specific check, a non-significant result is exactly what we want to see. By proving the interaction is definitively non-significant, researchers guarantee their regression lines are parallel, confirming the foundation of their ANCOVA model is perfectly solid. With the assumptions mathematically verified, we can finally evaluate the adjusted results of the experiment. This final ANCOVA table highlights two rows, the drunkenness covariate and the adjusted drink factor. The covariate's p-value is under 0.001. Directly below, the drink effect's p-value is 0.003. Controlling for drunkenness makes the drink type statistically significant. But we have a remaining critical step. We need to determine if this statistically significant effect is actually large enough to matter in the real world. Statistical software typically provides three effect size metrics: eta squared, partial eta squared, and omega squared. This matrix outlines criteria for selecting effect size metrics. With a sample under 30, omega squared is the optimal choice to prevent bias. The calculated value of 0.173 maps to a large effect. A p-value proves an effect exists, but calculating an unbiased effect size proves the intervention is powerful enough to warrant real-world application. We still have one final analytical blind spot. The ANCOVA proves a difference exists, but it doesn't specify which beverage is actually superior. Resolving this requires post-hoc testing. This method rigorously compares all individual group pairings against one another. For this dataset, we use Tukey's post-hoc correction to prevent false positives when group sizes and variances are equal. The Tukey post-hoc matrix plots the intersections between water, coffee, and Baraka. Looking at critical intersections, Baraka significantly beats water at 0.004 and coffee at 0.01. Conversely, water versus coffee yields 0.973, showing no significant difference. By systematically controlling for continuous covariates, ANCOVA rescued a failed experiment from random noise. It provided mathematical proof of a superior treatment, demonstrating that controlling for what you can't change is the only reliable way to measure what you can.